is Wesley Mon. I'm a first-year Master's of Public Policy and Management student at Hines College, and I'm also the 2023 Mobility 21 Transportation Center Equity and Inclusion in Transportation Fellow. Like I said, it just rolls right off the tongue. The Smart Mobility Connection Series is sponsored by the Traffic 21 Institute and the Safety 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It's also an opportunity for students like myself, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note this session is being recorded, and if you're joining us on Zoom, all of your microphones will be muted. If you have a question, feel free to just send it in the chat throughout. If you're in person, we have a small enough group, feel free to just raise your hand. And I would like to introduce today's speaker. We have Swarun Kumar. He's the Sathai Family Foundation Association Professor at Carnegie Mellon University's ECE Department with an affiliate appointment in the Computer Science Department, the HCI Institute, and the SciLab Security and Privacy Institute. Swarun heads the Laboratory for Emerging Wireless Technologies, the YTech Lab. He designs and builds novel systems to enable faster wireless networks and new services. Swarun is the recipient of the 2021 ACM SIGBED Early Career Researcher Award, the NSF Career Award, and Google Faculty Research Award. Swarun received the Google Sprouse Award for Best PhD Thesis in Computer Science at MIT and the President of India Gold Medal at ITT Madras. Please help me welcome Swarun as he tells us about his University Transportation Center project, Next Generation Radars, towards smart vehicles that see what the eyes can't see.
Introduction, and thank you everyone for joining. So as was mentioned, please feel free to raise your hands if you have any questions. Just interrupt the talk at any point in time. I'd like this to be a lot more free-flowing. So I'm going to talk to you today about next generation radars, but first just a little bit about what I do. So I lead the YTech Lab at CMU, and we work on next generation wireless systems. So all of this is work from my PhD students and some of my former PhD students. Actually, a good chunk of it is specifically work of my student Akash Prabhakar, who I co-advised with Anthony as well, Anthony Rowe at ECE. So what we do at the YTech Lab is build all things wireless, ranging from communication, interference, 5G and beyond, location tracking, sensing, security and privacy, a whole range of RF sensing, as well as communication systems. For today, though, I'm going to focus specifically on our work as it relates to transportation. And specifically, one aspect of wireless systems that you might not immediately think of, which is particularly crucial to future autonomous driving. And I think I'm hoping that this audience is already sold on autonomous driving being a thing that can eventually happen, maybe. One of the, I think, big questions, or the question that skeptics always raise about, every future car, every future vehicle being autonomous is would you trust sitting in a future autonomous vehicle and then driving through a fog or driving through mist, inclement weather, replace this by any sort of adverse condition, right? And would you still be comfortable, right, in that vehicle, right? That's sort of the broad question. But more specifically, to get to this vision of level 5 autonomous driving, which is autonomous driving, no strings attached, no override switch. Get the driver back on and get back on this behind the steering wheel to figure out what's happening, right? If you want to reach that level of autonomy in autonomous driving, it's very important to think about all of the different corner cases, ranging from road work, inclement weather, be it snow, fog, like I mentioned earlier, many, many more. It's just a few instances shown here. And the specific problem that I'm looking at as a wireless researcher is the perception aspect of this, which is, let's suppose that an autonomous vehicle, broadly defined, could be a ground vehicle, could be a car, could be a robot, could be UAV. Suppose it is navigating through a highly obstructed scene. This could be dust, smoke, fog. How can it do so? How can it still perceive the environment? And the hint for it is pretty obvious in the sense that I started introducing myself as a wireless researcher. And so there is a wireless solution to this, which is or rather a radio frequency solution to this, which is radar systems. So if you don't know what I'm talking about, I think this picture should be familiar to most of you. It's what you go through the airport, right? The machine that goes zoom all around and scans you, right? It's essentially what you go through at the airport is essentially a millimeter wave radar. It's the objective, again, is through obstruction perception, the obstruction here being clothes, and perception being trying to find out if you metal, right, for example, through the clothes. And the way this is achieved is again through a bunch of antennas sending radio frequencies. Metal responds differently or to those frequencies, and then essentially it's an imaging system, right? It's imaging through obstructions. So I must caveat though that this is a fairly complicated system, right? It has just the vertical bar that sort of sweeps through has 200 antennas, and then it's also sweeping around you. So effectively, the act of sweeping around makes it synthetically create more antennas around you, and as a result, you get even more resolution. So there are even more virtual antennas, if you will, right? Looking at you from all the different directions. This doesn't quite directly fit in the vehicular context. You can't, take one of those and put it on a car, and that's a bit of a challenge. So what we're really interested in here is to build something that's fairly general, right? Radio frequency-based sensing in a small form factor. That is something that can fit in the palm of my hand, hopefully. And there are systems that do this already on vehicles. This is the automotive radar, and one of the applications is cruise control, right? Like trying to find the distance to the vehicle in front, but there are radar systems that are more generally used in autonomous vehicular systems as well. There's a lot of fighting about where radars belong versus where LiDARs belong versus where cameras belong in autonomous vehicles. I'm not going to go into that. I'm a radar person, so I was going to talk about radar. And there are also other instances where radar is being deployed, including in smartphones, smart devices, and the like, right? For example, for gesture tracking. So it should be noted that none of these look like the 2-meter high-sized monstrosity that you go through with the TSA, right? The reason why that platform is so big is that essentially in wireless theory, right? The more antennas you have and the more spread out they are, the sharper the beam is that can scan the environment. So another way of saying it is more antennas means a sharper resolution. Think about it as if you can see the object from a lot of different angles, and as a result, you get a really sharp view of what you're looking at. Now, if you now shrink this to a smaller form factor, something that fits in the palm of my hand, a natural problem is that you go from this narrow beam now to a fatter beam, right? That can be, if you're going from meters to centimeters, right, that's going to be a significant reduction in resolution, right, by more than an order of magnitude as a result of that. So you get 15-degree beams as opposed to a half-degree beam. And now this is not going to be great at imaging things. There's going to be a limited resolution. So just as an example for something that we have in a later slide, this is a LiDAR in a typical office space, and you can sort of make, it's kind of obvious that this is an office space. You sort of see walls and some structure that resembles a floor plan, but the same thing on a radar looks a lot more cluttered, messy, and it's very, very hard to make out anything that's useful. So that's the trade-off, right? If you go to small form factor, you get much lower resolution, as well as also severe clutter-like phenomenon that emerge. So what a lot of my work has done is essentially push the limits of what's possible with a compact radar platform for applications, including getting closer towards level 5 autonomous driving, right? And here today, I'm going to give you a few different examples of projects that all relate to automotive in some way. First, we're going to talk about tire health sensing, and then road markers, and then imaging, the broader problem that we talked about. You might say, why tire health sensing? That's the first thing I'm going to talk about. So if you have a future autonomous car, you don't have somebody there regularly inspecting the tires of the car. right? So you do need some sort of an automated system to enable that as well. So what we built is a system called Osprey, which is a true mud imaging system for sensing tires, right? And this was in collaboration with Bridgestone, the tire company. So what we envision is, today most modern vehicles, right, have a TPMS system, which is a tire pressure monitoring system. So you know how much air there is in each tire. It would be nice if you also had a dashboard that told you, hey, the tire is too worn out, right, and needs to be replaced. And what's the overall health of the tire, particularly tread depth, among other things. Why? Is that important? Because if you don't take care of your tire, it's eventually going to be like this. Right? It's going to all of the treads are going to get worn out, and it's going to be a safety. It's going to cause safety problems. It's always nice to show those in videos and scare people. This is what happens if you drive on wet road in good tires, and then this is what happens if you drive on like these sort of completely worn out tires. Right? So it matters. With Bridgestone, one of the sentences that they said that stuck with me, it's of course branding, and I think it's a rehearsed line that they tell everybody who they talk to, which is like, we are the most important part of the car because we are the only part of the car that touches the road. Right? Yeah. So how does Osprey work? And again, it's fairly intuitive if you think about it. Now remember that I told you that cars already have these collision radars that sort of look forward, that look at the distance between them and the car in front. Why? Because you don't want to collide with it as a collision sensor, for example, or for cruise control. Now let's imagine taking that radar and making it face the tire itself, right? And so as a result, here's what you're going to get. Let's assume you get two distance measurements. One is the distance to the surface, and the other is the distance to the groove, which is deeper inside. Your tread depth measurement is therefore this distance to this groove minus the distance to the surface, and you're done. Why radar? Why not a camera or depth camera or anything else? Because it's a little bit of dust, debris, etc. that settles in the tire. Radar just penetrates all through that, right? Which is great. Okay, so then what's the catch? Like, why is this so hard, right? I think the main challenge that I'm going to talk about, right? Of course, debris is one. Is the resolution to which you need this. So if you imagine a typical automotive radar, right, it's not really trying to get millimeter scale tracking of the car in front, but when you're talking about tread depth, then millimeters start to matter, right? It's a very fine range over which tread depth operates, 2 millimeters to 20 millimeters in general. So that's a challenge. And of course, debris, there are different kinds of debris. They all have different forms of influence on the tire itself. So it's not as simple as I made it out to see. So let's try and understand how our solution works. So it also helps to start to think about what radar ranging actually is, how it actually works. It's a bit of a messy picture, but let's look at it this way. Right? Let's say there are two objects at two different distances related to the radar. What the radar actually measures is the distance between itself and the two objects, here the blue object and the yellow object. Essentially what it measures is the power received at different times. And you say, where does time come from? Essentially the radar is sending a pulse that gets echoed back, a pulse that gets echoed back. And further away objects get their signals reflected a bit later, and then that manifests itself as two different distances that you measure, right? So if this is the surface and this is the groove, that's essentially the two measurements that you are going to get. Now, in general, the resolution to which you can do that is inversely proportional to the bandwidth, right? That's just a standard formula that we have from the radar community. It also, another factor that's also important is the accuracy in this direction, which is in the angular direction, also called the azimuthal direction. That depends on something called the antenna aperture, which we'll also talk about, right? Now, it turns out, like I said, the radars that we have, which are small form factor, are extremely poor, particularly in the angle, right? They're 15 degrees, like we saw earlier, right? Because you shrunk the size of the radar. And then 15 degrees is not good enough to image a tire. The second problem that you have is that the range resolution is about, based on the bandwidth, it's about 3.7 centimeters, which is not bad for collision detection. It's good, but not certainly, over an order of magnitude worse than what you really want for tread depth measurement. So neither of these numbers look very good. So essentially, at this depth, right, like forget the tread, right? You're just going way too deep into the tire in terms of the amount of resolution you have, which is very, very poor compared to what you actually want. So how do we deal with this? So here's sort of a cool trick that exists for radar systems in general, and and has been shown on vehicular systems, except it's aerial vehicles, right? Airplanes, satellites as well. And the idea is kind of very similar to the TSA security inspection that you have, right? The idea of moving the antennas around, right? So in old school aircraft radar systems, you have this technique which is called synthetic aperture radar. The idea is the following. As an airplane moves, right, and even if it has a radar on board, it's getting different snapshots of the scene from different locations as it moves. And as a result, you have all of these signal measurements as the airplane moves, all of which could be looking at the same exact point in space. So rather than creating a radar, what you're essentially doing is you're synthesizing a radar as you move, right? You're synthesizing a radar, radar antennas as you move. And airplanes move a lot, and therefore these antenna arrays, virtual antenna arrays, can be really, really large, right? You're creating antennas arrays on the fly, right? It's called synthetic aperture radar imaging, or SAR imaging. So here there is no, it's very hard to make the radar move around, right? Just like the TSA thing, but you think about it, something is moving. The tire, right? So why don't we collect different snapshots of the tire as it rotates, right? And the end result is you get multiple signal measurements of the tire itself as it rotates. And as a result, that helps you image the tire. This is essentially inverse synthetic aperture radar imaging. The closest example to this is like when when you're doing sort of interplanetary measurements, when the planet itself moves, you can sort of leverage that for imaging. So the idea here is that we can now then focus on different sections of the scene, sort of similar to the airplane picture that I said. And then as the tire moves, we get all of these different parts of the tire that sort of rotate into that section. And as a result, we can focus on them. So I'm not going to go into the details of the math, but I just wanted to focus on one thing, which is that all of these signal measurements that we get really are measuring this parameter here, dA, the distance between the radar and that particular section on the tire. And remember, that's what's important. We're actually measuring the distance between different parts of the tire and the radar. And that's what gives us the tread depth measurement that we really care about, right? When we focus on different parts, which is the surface and the groove, right? So essentially, as this radar moves, and assuming you have multiple antennas here, you're essentially getting a matrix, a set of measurements as the tire moves, and then also measurements across different antennas, right, on the radar platform itself. And then you get this matrix. So effectively, our algorithm just collects these sorts of matrices for different sections of the tire as it rotates. And then essentially what we are going to receive is a combination of all of those different measurements that we get. And now suppose we are interested in the tread depth at any particular point in space, which is this blue square here. That's the depth we want to measure. So here's what we'll do. We kind of know how this particular point is going to traverse through the space, right? Because we know physically how fast the tire is rotating. And as a result, we can create some sort of an expectation. Had this point been at different distances, right? What would we expect in terms of the measurements from the radar platform itself, right? This is what I call the template measurement here, right? And then essentially what we do is we look at what we received, we have a particular expectation of what we received, we do a simple projection in the signal space, and that tells us, okay, is our estimate correct or not, right? The more they align, the better the guess. right? And effectively, what we can then do is we can do this correlation metric, right? For each possible depth of this particular point, we can see which in which instance does what we measure, right, compare well with what we actually got, right? And that gives us essentially the depth of this particular point in space. So the end result of this whole process is that we are essentially sampling all the different possible tread depths that the surface could be, generating a whole bunch of expected measurements, and then correlating that with what we actually received and see which one best fits our data. That's what we're doing. Right? What that could give us, essentially at the very least, is the radius of the surface itself, because the surface has a lot of prominent spaces. But if you're able to focus on the grooves, it could also give us a radius of the groove, although there's some problems that I'll talk about. Right? So here's sort of what it looks like, what this image looks like, right, for a particular section of the tire, and then you sort of start to see the features emerge, and we can start measuring this radius of the surface as a result of that. Now there is one problem though. So here's one specific kind of groove that is particularly problematic for us to measure, which is these sorts of grooves that go through the tire, but they are not changing very much. They're essentially the same depth throughout, right? And this is a bit of a problem because, like I said, it's nice to see some variation as the tire moves. But if there's nothing varying as the tire moves, you don't get the benefits of the higher resolution. So how do we deal with featureless quantities, like featureless grooves? And why we're particularly interested in this is because of debris. Now, if we have different levels of debris that's packing into these featureless grooves, now we have a bit of a problem because we don't know whether we are seeing the groove or we are seeing the surface. There's nothing that distinguishes the groove from the surface at these specific points in space. And so how we deal with that is construct a feature-rich groove. And the way we do that is essentially we add patterns on top of this groove, right? To create some sort of features, not just leave it as it is, right? And so the idea is, what can we add? What features can we add? It turns out, unsurprisingly, metal, particularly aluminum, right, is really good in terms of reflecting radars. And then you might say, okay, metal on a tire, how practical is that? Now it turns out, again, this is where conversations with Bridgestone helps. A tire is not all rubber. It's composed of metal, nylon, different compounds of rubber, everything, right? Essentially, if it were all rubber, there wouldn't be any structural integrity, right? You need something to sort of hold it together. So you do have, it is possible to essentially print metal into the tire. It's something that they do all the time to essentially ensure structural integrity of the platform itself. But what we essentially did was much more, simple, right? We just took strips of aluminum, right, and then laid them across the tire. Essentially, these were our features. And effectively, think about these like barcodes. They're in sequences of 0, 1, 0, 0, 1, 1, right? We could play around with the spacing. We could play around with the width and the location of the aluminum strips to get that particular effect. And as a result, even if there's some debris packed on there, we can look at these distinctive signatures that the metal would create. Now, the end result of this is now we're doing a pattern matching, and we know this pattern as well, right? So as a result, that really helps us distinguish between, find out these grooves that exist despite debris existing as well within the tire. So putting it all together, we now have this mechanism to measure the depth of the groove. We also have the depth of the surface, subtract the two, and that's what gives us the effective tread depth. So we went ahead and implemented this on my car, and so it was punished through Pebble, and CMU never reimbursed me for all the tire damage that was created. And so we did different kinds of debris, different kinds of all sorts of things, right? We got essentially a error under 1.5 millimeters across all of our different experiments, right? Depending on, of course, there are variations depending on exactly what kind of debris exists, as well as how much worn out the system was, right? But obviously, a system like laser would just be easily confused by debris. Okay, so this is a good segue into the next part of the talk. And again, feel free to raise your hands if you have any questions at this point, right? Yes.
Is this similar to how Formula One cars measure tire degradation?
So if you have access to the physical car, right? The easiest thing to do is to either place a penny in there or place an instrument in there, right?
But they measure real-time tire degradations, right?
So there are a few other ways in which people do it right now, which is especially when the car gets, when the car at least the Formula One context, a lot of the degradation happens because of heat, just the abrasion, like the very high heat. So there you can actually profile the temperature generated. Essentially, think of IR cameras, right? And then figure out if that's going beyond the limits, and then that gives you a sense of how much tire degradation is happening. In a regular car, the degradation is a lot more long-term. It's not sporadic like heat abrasion, right? And so it becomes a lot more hard to, do this, take that solution to the passenger car context, for example. And also, Bridgestone was more interested. So if you're really interested in why they care about it, they were not thinking really passenger cars. They were thinking about fleets of truck tires. So they have these truck tire replacement programs, and that's how they make most of their revenue. And they're interested in essentially making sure that these companies replace their tires more often, right? And this, it's kind of like their insurance play, basically, right? They can alert you that, hey, you need to replace your tire right away, and therefore make more money and sell more tires. Okay. Do you try and?
Do you want me to read that out?
Yes.
It says, do you try to compensate for the distance between the radar and the tire changing due to bumps in the road?
Yes, and actually that's an excellent question. There's actually the easy solution to that. Now, if the tire is jumping up, both the surface and the groove are jumping up by the same amount. So actually the tire jumping up and down doesn't really matter. Tire vibrating this way might matter a lot more, but this way it matters a lot less, and that actually helps us a lot, if that makes sense. Yeah, suspension. Suspension is not so bad for us. Okay, so let's then move on to through fog road markers. It's a different problem. The idea here being there's a fog, there's a stop sign. How do I know or there's maybe a temporary road sign that's been placed over there. How do I see it? Right? Can I just have a marker in the environment that will tell me that it exists? And obviously vision doesn't work here because there's a fog. So what we built is a system called Millimetro here. It's again the same idea. You have these radars on the cars already for collision. Can they also read barcodes, basically? It's smart barcodes, if you will, in the environment now that convey information. Like, for example, the ID of a road sign that contains information about what it is, where it's located, etc. Right? And we've built this platform. Essentially, it's relatively tiny. It draws very, very limited power, and which means we can just attach a battery to it and power it for 10 years. And it operates at the radar frequencies. And essentially gives you pretty good range, like 100 meters or thereabouts. So how does it work? It uses a concept called backscatter. And if you're not very familiar with it, here's sort of how it works. You have an antenna, and then you essentially have a switch that operates between two different modes. If the switch is off, you see that the tag is connected to some sort of a load impedance here. And so when the signal is sent, it essentially goes and hits that load, right? When the switch is on, you get this sort of a bounce back reflection process that happens, and so you get a response up. So think of it as a switch that you can turn it on and off to essentially make sure the object reflects or does not reflect. So remember, for example, in the earlier project, we had these aluminum strips, right, metallic strips, that always reflects radar. Now imagine you could have a device that can switch between sometimes behaving like aluminum, but sometimes behaving like paper. And you can programmatically figure out, electronically change that to zeros and ones. You can encode information. right? That's essentially how these operate, right? The cool thing about this is that this actually operates over a wide range of frequencies, and it doesn't matter what signal is being sent. It will just reflect it. And you can build tags for automotive radars, right? Although, I mean, tags of this nature exist already at lower frequencies, like RFID tags are being a classic example. Now, the problem, of course, is Wi-Fi and all of these, your current RFID RF backscatter systems operate here. We are actually moving here to the millimeter wave automotive bands. So it's either 20 and there's another band around 77, right? For automotive, which is much, much higher than what is traditional. And traditionally, if you think about it, for the higher frequency you go, the signal experiences something called path loss. It just gets attenuated very, very, very quickly. So how do you deal with that for millimeter wave? It's a natural question to ask. So one insight, of course, is that it's not, what we care about here is not exactly the absolute strength of the reflection alone. It's essentially how well you can distinguish between these two states, between the reflection state and the not reflection state, right? And if you look at the specific formula for that, it's called the radar cross section. That formula, to our advantage, is proportional inversely to wavelength, right? And as a result, you are going to, at higher frequencies, you can actually detect these sorts of backscatter devices pretty well, right? That trick really helps us distinguish between different devices. The other way to think about this is that if I have these two states that exist, assuming I switch between these two states a lot, just over time, you get more and more, it's easier and easier to detect these objects, and that helps us too, right? The second thing we can help to improve the range of the system, improve the performance of the system, is something called retroreflection. And retroreflection is not something that's very uncommon to road signs and traffic dots and things of that nature. Essentially, that's what makes your road signs and other objects, lane markers, etc., very reflective when your headlight sort of hits them, no matter how you drive, right? So the idea behind retroreflection is the following: if a signal arrives to the tag, let's say from the green car to this green tag, right? I guess I'll just have to use my hand. Then the reflection goes back in the same direction. That's what retroreflective means. You reflect back in the same direction that the signal hits you. And so here from this blue car, the incident wave comes in this way, and then the reflection is sent back along that same direction. So it's almost like it just sends back energy in the same direction that it hits the device, right? And that really helps us improve performance a lot. We get good accuracy, and also as a result of this retroreflectivity, we get very, very good range compared to a whole bunch of systems. That's how we are able to hit that 100-meter mark. If it isn't for retroreflectivity, all of the energy would get dissipated. So as a result of this, we can essentially build these sorts of markers in the environment that can help. It can help detect other cars, detect roadside markers, potentially detect pedestrians if they're wearing these, as well as there are a whole range of other applications, inventory, etc. If you're thinking about vehicles in like forklifts in a warehouse, for example, right? So how does it work? There's a whole bunch of details. I'm just going to sort of skim through it in the interest of time. There's this whole ultra-low power design with a coin-sized battery that's operating the switch on one hand. That's a retrodirectivity. You might say, how is that retrodirectivity achieved? We use something called a Van Atta structure. Again, the Van Atta structure is like a structure that's existed in the radar community for a while, but not quite in this backscatter context, right? So how it works is the following. It actually it's easy to visually explain. Let's say you have a signal coming in from a particular direction. You sort of see it exit from the same direction. The reason is sort of as follows. Think about a signal coming in from a particular direction. If you go back to that animation again, each wave comes in with a slightly different delay depending on which direction it came from. And now all you have to do is to create this array in a way that those reflections get back delayed the exact same amount, right? So essentially the flow of EM this way, the delays this way, manifest as the same delays in the other way, right? And if you can do that, you get retrodirectivity. right? That's what this design really ends up being. So you just have to architect all of these elements and these phase shifts that you inject in the system to create that effect. And so essentially what you're going to do in terms of mechanically is design phase shifts. Phase shifts are just another fancy way of saying delays, right? You make sure that all of these signals that are impinging it, you know that they experience a certain set of delays. The reverse signal also experiences the same exact set of delays, right? So if you see these sorts of weird, interesting patterns here between all of the elements, that's essentially the retroactivity that we are able to achieve as a result of this in our platform. And another thing that we have is that we have is how does it actually operate? Is it really powered by the automotive radars? Not exactly. We just attach a battery to it, and it just sends a barcode basically all the time, on and off, on and off, on and off, just broadcasting it all of the time, asynchronously. So it's just switching on and off between these two different states. And as a result of that, it doesn't matter, any radar can query it, and then it gets a response, and then it uses that response to decode the bits. The cool thing about this is that we are able to get extremely high level of localization accuracy. So normally a radar, when it sends a signal, all sorts of objects would reflect off it, right? But so would our tag. And when our tag reflects off it, because it does this on-off thing, there are all of these gaps that exist. And we can use the fact that these gaps exist at known points and at known intervals to decode these sorts of tags better. That's really what gives us a resolution to look at these individual tags. And as a result, we are able to recover the tag modulation, decode data, but also do location tracking because we now know exactly, we know exactly at what distance that particular tag is, and that helps us locate it, right? So what this actually mechanically means is that we look at this modulation in the time domain, we convert it to essentially what's called the range Doppler domain, Doppler being related to essentially distance and velocity, right? And as a result of this, we can then locate it, locate it both in angle as well as distance. And that helps us figure out where the tag is. So where did we evaluate this? A whole range of spaces on campus. This, I believe, is the East Campus garage. And then this is Fru Street, right? Where, which is good because we get a good distance. And then a whole range of buildings. So if you've seen a lot of if any of you park in the East Campus garage and if you've seen sort of weird things going on, we might be one of those people with weird PCBs and everywhere. And then we also tried different levels of mobility, this time it was not my car, and bikes, my students' bikes, which and then also different forms of obstructions, etc., right, to sense resilience to that. So here's how well our system performs. You get 15 centimeters of ranging accuracy. Now, remember, this is much further away. Your distance is up to 100 meters or thereabouts, and you get 3 degrees of azimuth accuracy, which is more than what the radar natively can do. And we can detect a whole range of cars up to around 100 meters or so, and even at 100 meters, you start to see that only about half the tags are detected, and then after that, there's a big fall off. We can detect cars, walking tags, many tags, whole range of other results are in the paper. I think let me show you a quick video of it. So here's it's sort of an AR visualization. The blue dot is just showing where the tag is, and if you see it, it's not here, it's not there. It's actually behind that door, right? So we can actually sense where the tag is even through multiple obstructions because it's radar, right? So mostly demonstrating the coolness of radar more than anything else, right? Okay, so next let me talk about through smoke 3D imaging for a little bit. And so far it's point applications, right? Sensing the tire, sensing roadside markers, but you might be interested in the more broader question, just can I just image the world using this radar? It's kind of overpromised and under-delivered a little bit, right? So let's try and address that problem. And so our objective is to make radar look like LiDAR. It's quite ambitious. And we built a system called Radar HD. The idea being that, hey, if I have, state-of-the-art camera, state-of-the-art LiDAR on a robot, and then it sees this beautiful scene, and then suddenly it's on fire, and then the whole environment is smoky, and now nothing would be seen, right? But radar can do better, as you saw, right, a few slides ago. So what's the problem? Radar would still see it, but this is what it would see, if you remember that earlier picture, right? This is the floor plan, and this is what the radar actually sees with lots of clutter, as well as lower resolution, right? So how do we solve this? I wish I had a more detailed answer, but then I'll run out of time. Deep learning, right? So we essentially threw radar data into a super resolution deep learning model, right? It's essentially a multi-layer U-net-based architecture, nothing too crazy, all right? But the main challenge there was in essentially finding out the right design point for these sorts of systems that have just essentially for super resolution have been designed for image data, but not really complex IQ radar data. So it was a lot of learning for us to figure out what's the right way to tune these to just work well with machine learning. When it's not pixels, but actually phases, and they wrap around with 360 degrees and all sorts of weird effects, right? So that's what we built, and it's a paper that came out in ICRA this year. Here's sort of a visual just to show what we did, and I'll just leave this as a teaser. So here's sort of what LiDAR sees and what radar sees on an otherwise identical scene. This is my computer acting out more than anything else. And you sort of see this is much better than what you saw before, right? Which is essentially the raw data and the raw heat map, right? So it's there's still some errors out there, but it works a lot better in terms of what it can see. And again, in a smoky environment, the LiDAR would see nothing. The radar just doesn't care about smoke or fog or any of those things. Okay, so I still have a bit of time, and the reason I left the bit of time away is to just talk about a little bit more about what we do, right? In our lab, it's just much more than these few applications. So here's one other system that we had, which is why should radar fight with anything? I'm trying to make the case for radar, but maybe the answer is radar should be combined with every other modality that we have on the car. So this was our camera plus radar fusion paper. The idea being that if you see this radar, particularly with super resolution, we can measure distance really, really well. So with millimeter, for example, there's a tag 100 meters away, and we can still see it at like few centimeters, like 2-3 centimeters worth of distance resolution, which is great, right? That's not natively what cameras are able to do unless you have a very long baseline, right? So can we essentially have a radar and a camera co-located and on a very tiny platform, and still be able to do very good depth imaging using radar for depth and using camera for the angular resolution? That's what we basically did. It was a system called Metamoran. If any of you watched Dragon Ball Z, okay, no, lost this audience. Right? That's where this comes from. It's basically a fusion technique. Right? And so that's what we do. We can do a lot better than what radar and camera can natively do as a result of that. Here's another project we have with some colleagues in Harvard, again in robotics. I know I say I do wireless systems, but a lot of my projects in transportation and vehicles end up going to robotics venues. This was a Wi-Fi based radar system. It was not really millimeter wave, although we're trying to use millimeter wave for it too. And here it's doing synthetic aperture radar, but the more classical one, where essentially the UAV here that's moving is doing this radar. It's essentially trying to go and rendezvous, which is the fancy robotics way of saying find that other ground robot over there. But that other ground robot is now hiding behind some obstructions. And so it's sort of doing a Wi-Fi based hide and seek, basically trying to find this this robot, and measuring what is AOA is basically the angle, the direction of arrival of the signal, angle of arrival of the signal, and then you see it sort of found its partner. Now you can use vision or Wi-Fi or whatever not, and you can go track it. It's not such a big deal. So you can detect people behind things even using more commercial off-the-shelf technology, not just radar. Right? There's a bunch of other research that we have. Again, different kinds of vehicular platforms. So we have a lot of collaborations with soft roboticists on building soft materials and then integrating them with backscatter platforms like Millimetro was. We're doing it for a bunch of on-body sensing applications. We have these smart pills that you can track through the body. But one cool project that we have right now are these soft robots that can navigate through pipes. We can track them, of course, using the radar. But the more fun thing about this platform is that it's not being, it doesn't have a battery on it. And you will still see that it is crawling and moving. And actually, it's crawling through a pipe, a plastic pipe. It's transparent just for visualization, but this could have been a non-transparent pipe. So how is this robot crawling without a battery through a pipe? It turns out you're using wireless. Any guesses? How can you wirelessly move something inside a pipe that you can't see, and there's no battery attached to it?
Magnets?
Magnets? Oh, no, I could guess. It's actually microwave heating. So imagine this is similar to a microwave oven. How does your popcorn pop? And with force, even though it doesn't have a battery, microwave energy is hitting it from the outside. So we are essentially using this sort of wireless to heat this metallic strip that you see here. And we can just send the right wave so that it's not a very high energy beam that just really focuses on this one particular point, and then we can make it move. So this is a different sort of project, and using wireless to control robots as opposed to using it to sense, which we always do, right? So it's another direction. And it has implications for soft robots because there are all of these heat-actuated soft robots where you use heat to move them, but there's always this laser gun or this heat gun standing right next to them. And then you're like, okay, you build this nice, small, battery-free robot, but then you need to always have a heat gun around. It makes no sense. So now we can microwave it. I don't know if that makes it any nicer, but at the very least, you can crawl through things now, right? Without much of a problem. Here's one other thing that we're doing, which is so I'm part of the $7 million NSF center that's right here at CMU with Brandon Lucia, VR Shekhar, Zach Manchester, who's in robotics, and Gauri Joshi, on essentially sending these small satellites in space. And these are also, you don't think about them as robots, but they look big, but they're actually this tiny, right? And they have these elements to actuate them too, so they can also move around and rotate to orient them better in space. And we're interested in building a lot of ground infrastructure for it. We're interested in satellite comms, satellite imagery, etc. with this platform. This actually connects well with another initiative that Akshita and myself are leading, which is we have the newest CIT Moonshot, which is a compute and communication for all initiative where we are trying to collaborate with 16 faculty, John is one of them, spread across CMU Pittsburgh and Africa to bridge the digital divide, which is making internet available for all. And one of the hammers that we are using is satellite connectivity, but among a whole range of other things as well. And transportation is very much a part of our story because one of our colleagues is just looking at how do you get Uber and how do you get transportation in like the middle of nowhere when you don't have the critical mass, you don't have the market availability yet of these sorts of platforms. So let me conclude with saying that even intellectually, there are tons and tons of questions here, particularly when you don't just think about one device, but a swarm of devices, a swarm of vehicles. So what can we, if you have a whole group of like firefighting UAVs or fleet of autonomous cars, can they exchange information? to get better sensing? Can you really build up this nice visual map of the world, and how can that influence both communication and sensing? Why think so narrowly as, I mean, I started out saying, hey, I'm a wireless person, but why think just RF? Why not think of embrace all EM frequency bands, everything from very, very low to very, very high, which is cameras and beyond, and think about what is the one solution that sort of combines all of these. I think that's, there are plenty of open questions, right, beyond what our own silos. So thank you so much.
Does anyone have questions?
Yeah, I wondered what happened with the tire gauge. What level of development is that at, and is Bridgestone going to commercialize it?
Yes, they are actually. So they patented it, and they're currently rolling out some simpler version of it on their truck fleets, but it's still in the process of
Development.
Yeah. This was like a couple of years ago, and so there's this long process between between that and them adopting it. But they're moving forward with it.
Okay, great.
I have a question. I heard about this company LunaWave, which is using a Lunenburg lens for radar.
Yeah.
Have you heard about that?
Yes.
And how does it relate to what you're doing, or is it?
It's another, so there's a lot of work that's emerging on this broad concept, which is, can we build smart materials for millimeter wave? Because it's sort of weird. Millimeter wave is exactly in the middle between two different frequency spectra. So Wi-Fi and so on, you don't think of them as similar to light. They can penetrate through things very freely, and lensing is possible, but the lens has to be building sized. So you can't build practical lenses for it. In optics, lenses are so common, right? And all sorts of materials, using materials is so common to improve optics in general, right? I just don't want to say lenses, but it could be mirrors, could be a whole bunch of other things, right? Millimeter wave is right in the middle, so it shares some properties with light. It shares some properties with traditional RF frequencies like Wi-Fi and the like, and cellular and the like, most of cellular and the like. And so as a result, there's potentials to build, take some of the learnings from optics and bring it here, but there are challenges too, right? So it's not going to work as well as optics, and there are going to be new challenges there. So that's sort of where this company is trying to play, and there are a whole bunch of players who are trying to get better radars by adding smart materials to it, more broadly speaking. The thing that has fundamentally changed is the availability of these sorts of radar platforms, much more commoditized, because radar used to be you had military radar for a long time, but you didn't have radars on smartphones until recently, right? And that's changed the game for sure.
Well, thank you so much for sharing your work with us. Let's give another round of applause. And thank you all for attending today. As I mentioned earlier, the slides and a recording of this session will be posted on the Safety 21 What's Happening page for students in the room. If you're interested in getting involved in more transportation initiatives, there is a campus-wide transportation club that I'm an incoming officer of, so check that out on Tartan Connect. And our next seminar will be on Friday, October 13th, and will feature Rachel Burson from the Robotics Institute, so watch your email for an invitation to that. Again, thank you so much for attending our session today, and feel free to reach out to us with questions.